They expected to find a dead zone, a place so compressed, so cold, so starved of light and nutrients that life would exist only as a rumour. What they found instead forced a quiet but significant revision of what we thought we understood about the limits of biology. This is the story of what happens when a team descends into the deepest trench on Earth, and the environment refuses to cooperate with the theory. The Hadal zone begins where most maps simply stop. At around 6 kilometers below the ocean surface, the seafloor drops away into long, narrow, V-shaped depressions that reach as deep as 11 kilometers. The name comes from Hades, the ancient Greek god of the underworld, and the naming committee was not being poetic. They were being precise. These trenches occupy less than 1/4% of the world's seafloor area, and yet they account for more than 40% of the ocean's total depth range. That is not a statistical curiosity. That is a compression of extremes into a sliver of geography that almost no instrument has ever reached. Most Hadal habitats are concentrated in the Pacific Ocean. The largest and deepest of the world's ocean basins holds the majority of the 46 individual Hadal habitats identified worldwide. To descend into one is to enter a world where pressure does not increase in a straight line. At 90 meters depth, pressure is already 10 times what it is at the surface. But moving from 6,000 meters all the way down to 11,000 meters, the full span of the Hadal zone, only doubles the pressure again. The physics are counterintuitive, and the biology that emerged inside them is stranger still. Consider what a living organism faces in this environment. There is no sunlight at all. Temperatures are low, nutrients are scarce, arriving not from photosynthesis below, but as fallout drifting down from the upper ocean, fine sediment, and occasional landslides along the trench walls. Most organisms in the Hadal zone are scavengers and detritivores. They eat what falls. They wait. They process the remnants of a world 11 kilometers above them. And yet, as of 2020, more than 400 species have been documented in Hadal ecosystems. This is what changed the expectation. The early expeditions did not anticipate it. Historically, scientists did not even recognize the Hadal zone as distinct from the abyssal zone immediately below it. It was during the early 1950s that the Danish Galathea Thesson and the Soviet Vityaz expeditions, working separately, detected a clear and documented shift in the community of life at depths between 6,000 and 7,000 meters. Something was different down there, different enough that a zoologist named Anton Fredrik Brun proposed a new classification entirely in 1956, drawing the boundary of a new zone at 6,000 meters depth. The Hadal zone had been formally recognized. And with that recognition came the question that still drives research today. How is anything alive down there at all? And what does that life look like? The answer is not simple, and the instruments that reach this environment are operating at the edge of their own physical tolerances. Sampling equipment, camera systems, landers lowered on cables to the trench floor. Each one represents a compromise between what scientists want to see and what the pressure allows them to build. Evidence from the Hadal zone is therefore always partial. A species detected in one trench does not confirm its presence in another. A sample collected from the sediment tells you what was there at that depth, at that location, in that moment. The Hadal zone contains 46 distinct habitats, and they are not identical. What the evidence does show is a biology shaped by pressure in ways that are still being worked out. Organisms adapted to Hadal conditions carry stabilizing osmolytes inside their cells, compounds that protect protein structure against the crushing force of the water column above. Their cell membranes carry unsaturated fatty acids that maintain flexibility at temperatures and pressures that would rigidify normal biological membranes. These are not hypotheses. These are documented biochemical observations drawn from collected specimens. The adaptations are real, but the relationship between pressure and metabolic rate across Hadal species is not consistent. The evidence does not support a single clean model. Different species respond differently, and the science reflects that complexity. One of the more unexpected observations from Hadal research is the phenomenon of gigantism. Certain amphipods, mysids, and isopods found in the Hadal zone reach sizes substantially larger than their shallow water relatives. At the same time, other Hadal organisms displayed dwarfism. Nematodes, copepods, and kinorhinchs trend smaller than their counterparts elsewhere. The trench appears to push organisms toward extremes in both directions, though the mechanisms behind this divergence are not yet fully established. Fish, it turns out, do live in the Hadal zone, though their diversity is limited. Snailfish, cusk eels, cutthroat eels, grenadiers, pearlfish, and eelpouts have all been documented at Hadal depths. There is a theoretical maximum depth at which vertebrate fish can exist, related to the limits of the biological structures that allow them to function, though that boundary has not been precisely confirmed. What is known is that some snailfish species have been recorded deeper than any other vertebrate, at depths that would have seemed implausible before the expeditions that documented them. About 94% of the Hadal zone exists within subduction trenches, places where one tectonic plate is sliding beneath another. This geological origin matters for the biology. The V-shaped geometry of these trenches funnels organic material downward. Food concentrates in the deepest sections. Communities in the trench axis can be denser than communities higher on the walls, which is itself a reversal of the expectation that life simply decreases the deeper you go. The deeper, in some documented cases, is where the food ends up. The exact unresolved question sitting at the centre of Hadal science is not whether life exists in these trenches. That question was answered, incrementally and with collected evidence, over decades of expeditions. The unresolved question is more precise. How does life move between trenches? And why do some Hadal species appear at comparable taxonomic levels across multiple trenches while still being highly endemic at the species level within individual trenches? The same group of organisms, recognizably related, distributed across isolated deep trenches separated by thousands of kilometers of abyssal plain, yet distinct enough at the species level to suggest long periods of reproductive isolation. How did they get there? When? By what route? No expedition has yet answered this fully. The tools required to observe larval dispersal across abyssal depths, to track population genetics across separate trenches, to time the colonization of a new trench after it forms, remain at the edge of what current technology can deliver. What the expeditions have delivered is this: a corrected picture. The deepest places on Earth are not sterile. They are not simply waiting for life to arrive. They are ecosystems with structure, with endemic species, with documented biochemical adaptations and observable community dynamics. They are ecosystems we have sampled from only a fraction of their total area, with instruments that tell us what exists in a very small area of a very narrow trench at a very specific moment in time. The Hadal zone covers less than 0.25% of the seafloor. Everything documented from it has been retrieved from a geography smaller than many countries, at depths most technology cannot reach. The 400 species catalogued as of 2020 are almost certainly not the final count. They are the species found so far in the places we have managed to look, with instruments capable of surviving the pressure long enough to return a sample. the trench keeps the rest of its inventory to itself, for now.